All right, looking at exercise 4 and 5. Exercise 4 and 5 would be a comparable type free response question where you're taking the experimental data as shown in exercise 4 and then later on relating it to mechanisms in exercise 5. So I kind of separated them but tried to design this to look similar to one of the types of free response questions you might see for kinetics. And it involves the experimental data like this. The other form or other type of free response question you might see are the integrated rate log graphs where you're doing the natural log of the concentration versus time, inverse of the concentration versus time, and working some of those integrated rate law problems. And we will look at maybe reviewing some of those next week. All right, so here we're going to write the rate law, we're going to determine the overall, and do the calculation for the rate constant. So let's start with the rate law. We're given experimental data. That means we need to use the different experiments to figure out the order of the reactant for each reactant. We have bromine and we have nitrogen monoxide. So looking here for our nitrogen monoxide, which two of the experiments, because remember this is experiment 1, 2, and 3, which two should I use to find the nitrogen monoxide order of reactants? We want two experiments where the only thing changing is the nitrogen monoxide. We want the bromine concentration to remain the same. Yeah, so we want to use 1 and 3. Now I showed you the full equation before, but here we're only going to use the stuff for nitrogen monoxide because we know the bromine will cancel out along with the K's. So we have our third experiment. Going to do that first. The rate goes over here. Over our first experiment, the initial rate, 1.6 times 10 to the minus 3. That's going to equal our concentration here, 0.2 raised to the n, over our concentration here, 0.1 raised to the n. Now for the mental math, this is how I do these when they're both to the power, of minus 3. You could easily just move them both over 1 decimal, so that ends up being like 64 divided by 16. It's a much easier number to work with. So obviously this is going to go to being a 4. And then 0.2 divided by 0.1, that's going to be 2 to the n. So our order of reactant for NO happens to be a what? What is the order of the reactant? 2. That's pretty good and easy. Okay, we got that one. Check. That's for nitrogen monoxide. Now let's look at the bromine. The initial concentrations here for the initial rates method. Which two experiments do I want to use for my bromine? 1 and 2. Yes, I agree. 1 and 2. We definitely want to do 1 and 2. Because the concentrations are changing here, but for the nitrogen monoxide, they are remaining the same. So setting this one up, we're going to do 3.2 times 10 to the minus 3 over 1.6 times 10 to the minus 3, and of course, 0.2 raised to the m over 0.1 raised to the m. Once again, think about this like it's 32 divided by 16 because those would both move and cancel. So this is going to be 2 equals 2 to the m. So what is our order of reactant for our bromine? That one is going to be a 1. Very good. So this is for the bromine over here. This one over here was for the NO reactant. Now we can write out our rate law. Our rate law is the rate equals K times the bromine times the concentration of the nitrogen monoxide squared. Bromine is first order reactant, nitrogen monoxide is second order reactant. Very good. Now, based off of that rate law, where we had K equals How do we figure out the overall order of the reaction? Overall order of the reaction here. What do we need to do? Remember, this is like an understood one here. So what is our overall order of our reaction? It is going to be 3 because basically that's all you do is you add up the orders. So that's 1 plus 2, that's going to give us 3 for our overall order of reaction, excuse me. Now, so that would be for B. Calculating the rate constant K. All we need to do for that is use our rate law that we've just created, that we got from the experimental data. We know this is the bromine to the first order and the nitrogen monoxide to the second order. And it really doesn't matter which one you pick. You pick one of the experiments to plug in the information to solve for K. You can choose whichever one you want. I'm going to do, say, I'm going to do experiment 3. That's the one I'm going to plug in. You can try a different one and see if you get the same number that I do, but you should. 6.4 times 10 to the minus 3 equals K times, here's our bromine, oops, not 1.0, 0.10, and our 0.2 squared. Get out your calculator, let's do that math. So 6.4 times 10 to the minus 3 divided by 0.1 divided by 0.2 squared. And for K, I'm getting 1.6. Somebody do a different experiment and also get 1.6. Hopefully you did try a different one than me and see if you got your 1.6, but it should be 1.6. Now, don't forget, anytime they ask you to do a K, units are important. They always make one of the points the units, which is, I know, of course, seems silly, but the easiest way to do the units instead of trying to plug everything in is to use the equation, right? N minus 1 times the T, where N is that overall order of the reaction. Like so. So what was our overall order again that we figured out? 3. So this is going to be 1 over M3 minus 1 times our time, and it tells us seconds up there, so this is seconds. So our units should be, yes, the units should be n to the minus 2 times s to the minus 1. Or if you want to write it as the fraction way, they will accept that. You could write it like this. Still acceptable. Either way, it will work. So that's the first part of this type of free response where they give you the experimental data, you calculate a few things. They might even throw in one of those average reaction rate type things and leave one of the boxes in the table blank or something. You'll see variations of this. But now that we know our rate law, information about it, they could tack on something like this at the end, where they give you some mechanisms, and sometimes it's 2, sometimes it's 3, that you have to choose from and decide which mechanism applies to our rate law. Now we know experimentally the rate law came out to being here. Bromine's first order, nitrogen monoxide is second order. Now we look at our 2 possible mechanisms that are proposed here, and we have to decide which one actually works out. Go back to the mechanism requirements. Let's take a look at those. What are the 2 mechanism requirements that must happen in order for us to choose the right mechanism? What's the first thing? What's the first requirement?
Oh my gosh, these are like the 2 ones I don't put out.
What are the 2 mechanism requirements? First one, Anyone? The mechanism must agree how? What's the first thing? Or it must match the balanced equation. Thank you. It must match the balanced equation. So let's take a look here. Here's our balanced equation. We got bromine, 2 nitrogen monoxide, 2 of the NOBRs. Well, first mechanism here. Looks like we have an intermediate of bromine that will cancel. So we have the Br here. That's going to be our intermediate. And if we look and calculate, we have 1 bromine, 2 nitrogen monoxide, 2 NOBRs. Check. This one works. That one satisfies the balanced equation. Let's look at the second one and make sure it satisfies the balanced equation. Looks here we have NOBR2 and NOBR2 here. So those are going to end up being the intermediate for this one. And let's check, we've got Br, 2 of those, and 2 of those. So check, this one also works for the balanced equation. Both of them meet that requirement. Now what's the second requirement that it must meet in order to be consistent with the rate law?
Must agree with the experimentally determined rate law.
So it must agree with the experimentally determined rate law, which we know to be first order reactant for bromine, second order reactant for the nitrogen monoxide. Now when we're trying to determine if it agrees, we need to look at the slow step or the rate determining step to write out the rate law. So that's what we're going to do. We're going to look at the slow steps. So here, the slow step is the first step. So that's easy to write out the rate law when the slow step or the rate determining step is the first step. All you got to do is count your reactants. And remember, the amount of them is the order of the reactant. So if I'm writing out the rate law for this one, that's going to be 1 bromine, 1 nitrogen monoxide. So, oh, forgot my K, hold on. Let me put the K in there. So this is the bromine, this is the nitrogen monoxide. Does that agree experimentally with our determined rate law? Does that go? Does it match? It does not. Guess what? Number 1 definitely is not going to work. But we still have to justify our answer, so we need to figure out number 2. And guess what? Number 2, they gave us one that has the steady state approximation. Okay, and I also need you to change this. I forgot to do that here. Make this equilibrium, because this is supposed to be a fast equilibrium here for that first step. It's supposed to be a fast equilibrium. So just make it a double arrow, because that's what it's supposed to be, fast equilibrium there. So we have to do the steady state approximation, and this is the one that's kind of a pain. So let's work through the steady state approximation. Recalling that the slow step is the important one, so I'm going to go ahead and write out this rate law, even with the intermediate, so I can substitute in later. So that's going to be rate equals K times NOBR2 times our NO, like so. So later I'm going to substitute in. Now remember, we're using the steady state approximation for our first step. The reason why we can do this because it's a fast equilibrium. That means the rate of the forward equals the rate of the reverse. So if the rates are equal, we can set them equal to each other. So over here, we're going to have, and I do K forward times our concentration of our bromine. These are the 2 reactants in that particular part going forward, going this direction. But that's also going to equal the rate going the other direction, where this would be the reactant. So K reverse, like so. And therefore, those are equal to each other since they're in equilibrium. And that's why that works. But we need to be able to substitute in for our intermediate in the slow step. So I need to isolate the intermediate here by getting rid of the Kr over to this side. Now, I'm ready to take this and substitute it in. Okay, this is going to get substituted in over here. we go ahead and do that. We do the rate, and since this is the second step here, you can make that K2. That's going to equal K2 times the KF substitution that we're sticking in here, like so, over the KR, and then times our NO, the second one in here, like so. And remember, this whole section just changes over into the new K, and we get the rate equals K times the bromine, first order, which works. And then since now there's two NOs, that one agrees experimentally with the rate law. So justifying the answer, you can show the substitution, like so. That steady state approximation shows the substitution here. Now, if you want to add in, for the justifying, you can definitely explain it, which is what I do here. Both mechanisms agree with the overall reaction. Steady state approximation where BR2 and NO substitute for the intermediate. Slow rate determining step shows that BR is first order and NO is second order, which agrees with our rate law. So good way to justify here in order to tell that we're going to end up with the second mechanism would be consistent with this particular reaction.